Whenever a magnetic flux linked with a coil changes, so there is an induction of EMF in that coil. So if you change a magnet position near to a coil, you will find that a current is induced in that coil. So hello students, welcome to my next online class. So in this video we are going to learn a new chapter, that is electromagnetic induction, and under these topics some few very interesting subtopics, that are Faraday's laws, induced current, Lenz's law, motional EMF, one by one, right? So you see, whenever a magnet is brought near to a coil, now if I consider this is a coil and a magnet is brought near to it, now when you change the position of this magnet from left to right, a current will be induced in that coil, right? So this is called electromagnetic induction, and this is given by Faraday's laws. So Faraday is saying that if you change an EMF directly proportional to change in magnetic flux, that means more you move the magnet near a coil, so there will be change in magnetic flux, magnetic field lines, so due to which an EMF will be induced in the coil. Now you see, this direction of current in the coil, whether it will be clockwise or whether it will be anti-clockwise, that is given by Lenz's law. So whenever there is an induction of EMF due to movement of the magnet, an EMF is induced, that is from Faraday's law, and if EMF is induced, a current will also be induced in the same coil, and the direction of this current is given by Lenz, right? So Lenz is saying that whenever a north pole of a magnet is brought near to a coil, right, so the near face of that coil also develops north pole, and north pole means anti-clockwise direction of current. A current will be passing through in the coil in anti-clockwise direction. Similarly, whenever a south pole is brought near to a coil, so the current in that coil will be clockwise, because south pole means here clockwise. The near end develops also south to oppose the motion of this magnet. So south pole, when it comes near to a coil, so it develops a south pole here. Now as the south pole has formed here, so there will be a clockwise current, right? So clockwise, when I say, you see the current will be moving up like this. So these are the few topics which we will be learning in this video, so stay tuned and watch the video till the end. Suppose a bar magnet is made to move in forward direction as well as in backward direction in front of a coil. So it has been seen that due to motion of this magnet, a current is induced in this coil. So whether it will be clockwise or sometimes it is being anti-clockwise. So this direction of current is being seen by galvanometer, which is connected at both the ends of that coil. So this is called electromagnetic induction. So whenever a magnetic flux linked with that coil changes, an EMF is induced in that circuit, and this change will last as long as there is change in magnetic flux. If you stop moving the magnet, there won't be any EMF produced, and therefore the induced current will also stop. That means no current will be passing through that circuit. So EMF is directly proportional to change in magnetic flux, and whenever a current is induced in the coil, it always opposes the motion of this bar magnet. That means it will try to stop the motion of the bar magnet by developing same pole near its face. Like if I consider south pole is moving towards the magnet, here when south pole is near to the first face of this coil, so the first face will develop a south pole. Now here you see, if a south pole is coming towards a coil, so near end of this coil will also develop south pole. Now south pole, when I say, this is clockwise current, so a clockwise current will pass through this coil. So as a clockwise current is passing through this coil, so this will oppose the motion of the bar magnet. Similarly, if you bring a north pole towards a coil, a bar magnet with its north pole, if it is facing a coil, the near end of a coil will also develop north pole. Now north pole, when I say, that is anti-clockwise direction. Okay, so you see, this is the anti-clockwise direction of current will pass through this coil. So this direction of electric current is given by Lenz, that is Lenz law. It states that the direction of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux producing it. So when there is a movement of a magnet, a current was induced in the coil. So a current, as current is passing through that coil, the direction of current may be clockwise, may be anti-clockwise. If it is clockwise, then you have to understand that a south pole of a magnet is near to it. If it is anti-clockwise, then you have to understand that the north pole of a magnet is towards its first phase. So this direction of current was given by Lenz law. When a conductor of length L moving in a magnetic field B with a velocity V in a perpendicular magnetic field or a uniform magnetic field, then the EMF induced in that conductor is given by E is equal to BVL, or you can say EMF induced in that length of a conductor is BLV, and this EMF which is induced in that conductor is called motional EMF. You can see in the diagram, you see this is the length. If I consider this is the length of the conductor, this one, this is the length of the conductor, and it is moving with a velocity V, and cross sign indicates that this is a uniform magnetic field. So when this conductor of length L is moving in this uniform magnetic field, an EMF is induced in that conductor, that is given by motional EMF, that is BLV. So Lenz law gives the direction of induced EMF in the circuit, and it is always opposite, or it always opposes the cause due to which it is produced. So motional EMF, as already I have told, it is given by BLV or BVL. And when this metallic rod of length L rotates about one of its ends in a plane perpendicular to the magnetic field, then the induced EMF is also given by E equals to half B omega R square, right? Where B is the magnetic field, omega is the angular velocity, and R is the radius of the disc. Fleming's right hand rule. If we stretch the thumb and the forefinger and the central finger of the right hand in such a way that three are perpendicular to each other, thumb represents the direction of motion, forefinger represents the field direction, that is magnetic field, and central, that is the ring finger, will represent the induced current. So in Fleming's right hand rule, the current induced is given by I equals to E by R, where E can be written as here E naught, and E naught is given by NBA omega sin omega t. Okay, sin omega t, where omega is the angular velocity. So that in place of E you see, it is substituted here NBA omega sin omega t by R, where R is the resistance of that circuit. So NBA omega by R can also be written as I0, that is I naught. So I equals to I naught sin omega t. Just you need to remember this expression. So this expression it will be used in numericals. So you see, let us consider this is a uniform magnetic field all around, and in this uniform magnetic field a sheet is being placed, a conductor is being placed. Now when you will move this conductor, when you will change the position of this conductor from left to right, then this conductor will get heated up, and current will start passing through that conductor. That means we can say a circular loop current will pass through this conductor, right? So this is called eddy current. So when a piece of metal is placed in varying magnetic field or rotated in a high speed, that is in uniform magnetic field, a current will set up like a circular loops. So if this conductor is made to move left and right, okay, in a uniform magnetic field, a current will start flowing through this conductor. These currents are called eddy currents. And this eddy current, because of this eddy current, the conductor will get heated up. Now once it gets heated up, that loss of energy is called eddy current loss or eddy loss. So you see, let us consider there is a coil and this coil is carrying current. As the coil is carrying current, so there will be change in magnetic field all around, and we know change in magnetic field will induce EMF in the same coil. This back EMF produced in the same coil is called self-induction. So the phenomena of production of induced EMF in the circuit due to change in current flowing in its own. That means when a current is flowing through that coil, due to its own current, an EMF is induced in the same coil. This is called self-induction. So you see, when the current in a coil is changed, the back EMF is produced in the same coil. This phenomenon is called self-induction and it is denoted by L. So N phi is directly proportional to I. So more the current it is flowing, so more there will be magnetic flux. And if we substitute this proportionality sign, we will get N phi equals to Li. Or we can say, if we differentiate both sides with respect to dt, so here also we will get dt, right? Now d phi by dt is called EMF. So change in magnetic flux is called EMF here. So we will get N E equals to L di by dt, right? L di by dt. So if you cross multiply, you will get the EMF. If the number of turns of the coil is 1, then we can say that E equals to minus L di by dt. So this was self-induction. So self-induction through a solenoid is given by L equals to mu r mu 0 n square Al. So mu r is called relative permittivity, and here mu 0 absolute permittivity, n is square number of turns, and A is the area of cross section, and L is the length of the coil. Mutual induction, the phenomena of production of induced EMF in the circuit due to the change in magnetic flux in its neighboring circuit. Like for example, if we have two coils here, like in a transformer, if you change here current in one coil, due to change in current in one coil, and EMF is induced in the other, right? So this is called mutual induction. So change of magnetic flux in a primary coil, if it induces an EMF in the secondary coil, so that is mutual induction. So you see two coils are being connected by a copper wire. So when two coils are placed nearly and the current in one coil, that is primary coil, is changed, the magnetic flux linked with the neighboring coil, that is the secondary coil, changes, due to which an EMF is induced in the neighboring coil. So here it is given by phi is directly proportional to I, where phi 2 is directly proportional to Mi2. So similarly here EMF induced will be minus M di by dt. Okay, so M is the mutual induction, coefficient of mutual induction, you can say here. So these are the expression. That means when two coils are connected, so they have self induction of L1 and L2. So what will be the mutual induction then? M equals to root under L1 L2. So this is also called coupling. and inductance of a solenoid is given by M equals to mu 0 N1 N2 A by L. Next we have here transformer. So transformer is a device which converts low AC voltage into high AC voltage or high to low. So it can step up the voltage, it can step down the voltage. In step up transformer, the secondary voltage is always greater than the primary voltage, as number of turns in secondary is more than the number of turns in primary. Similarly, in step down transformer, secondary voltage, that means output voltage, is always less than that of input voltage. So to make that one, what we do, we make the number of turns in output voltage as less. So number of coils is less in output voltage than that of input end. So the wires are also made thick and thin in this transformer. AC generator is a device which converts mechanical energy into electrical energy, which is based on the phenomena of electromagnetic induction, and it is given by EMF equals to NBA omega sin omega t, where omega equals to angular frequency, that is 2 pi f, and E naught is said to be as NBA omega, right? So these notes you need to write in your exercise copy as well, and we will see some numericals now. Like you see, there is a question in 2001, a magnet is brought near a coil. What will be the direction of current in that coil? So as I have told, when a north pole is brought near to the coil, north pole means here anti-clockwise direction. So near end of the coil also develops north pole. So north pole means here anti-clockwise direction. You see the direction of current is anti-clockwise, right? That will be in downward direction here. Similarly, if you bring a south pole near a magnet, then the direction of current was clockwise. In that case, the direction of current was in upward direction, that is clockwise, right? Now when north pole is brought near, the direction is anti-clockwise direction. So anti-clockwise direction means north pole. When north pole is brought near to it, when south pole is brought near to the coil, then it will be clockwise. This was given by Lenz law. So similarly, we have one question here. So when you read the question, you will find that there is a length of a conductor of 40 centimeter. It is made to move in a magnetic field B with a velocity V. So what will be the EMF induced in that conductor? So it is given by E equals to BLV. Substituting the value in the formula, we will get 0.2 volt. So what will be the direction of induced current in that length of the conductor? So induced current flows from D to C. So this is the direction of flow of current, or you can say that is in anti-clockwise direction. That is D to C, C to Q, Q to R. So anti-clockwise direction. Same here, a long straight wire carries a current of 3 ampere. Find the magnetic field strength at a distance of 10 centimeter. You see, this is a straight wire which is carrying a current. So at a distance of 10 centimeter, what will be its magnetic field? So I is given 3 ampere, R is given 10 centimeter. 10 centimeter means 10 by 100, that is 0.10, and mu naught value we know, that is 4 pi into 10 to the power minus 7 Newton per ampere square. Substituting in the formula, B equals to mu naught I by 2 pi r. So 2 pi r we have considered because now we need to find the magnetic field at its center. Like this is the circular coil. So what will be the magnetic field? Because it is an equidistance from both the ends, right? So as it is equidistance, so we need to use here mu naught I by 2 pi r. But as already I have told, if the point was here, then we could have used here mu naught I by 4 pi r. Substituting the values in the formula, we will get the answer. This is a very good question here, you see. So in the question it says that find the magnetic field at the center of the square of side A carrying current I. That means here let us consider there is a square. Each side is carrying current I here with the side A. So what will be the magnetic field produced at the center? So you see this point O is an equidistance from both the ends, that is A and D. So first we will find magnetic field due to one side, then whatever answer we will get we will multiply by 4. So formula stands by B1 equals to mu naught by 4 pi r sine alpha plus sine beta, where alpha and beta is the angle subtended by the center with both the ends. Alpha is also 45 degree and beta is also 45 degree because it is a square, and at the center it will subtend 45 degree and 45 degree. So after substituting here, sine 45 is 1 by root 2. So and in radius, you see the radius between, if the total distance is a here, so half of the distance from O to one side is a by 2. So radius is here a by 2. So we have to substitute in this formula. After substituting here, we get this expression, that is mu naught I by pi a root 2. And there are 4 sides are there, so 4 side is producing a magnetic field at the center. So whatever answer we got for B1, we multiply by 4, then we will get our expression. So similar type of numerical it comes in board, like they might give the quantity or the magnitude of current and the side of a square, and they will tell you how much magnetic field will be produced at the center. In that case you have to solve. So one more question we have here. So in from a cyclotron like, so in a chamber of uniform magnetic field of 8 Gauss is maintained, an electron with a speed of 4 into 10 to the power 6 meter per second enters a chamber in a direction normal to the magnetic field. Describe the path of the electron. Mass of the electron is also given. So path of the electron means they are asking you to calculate the radius, that is mb by bq. So in the cyclotron we have seen the radius of a path of a cyclotron is given by r equals to mb by bq. Substitute all the values, you will get the answer. Just in notes I have mentioned, so that you can just, you have to practice bit, you have to learn nicely. Okay, so I'm not going much detail here because now let's move to next question here. So you see there is a wire which is carrying current, and a rectangular coil is also carrying current which is placed near to that wire. So how much force will exert a wire on that rectangular coil? So that one we need to calculate. So what is the, you see last line when you see what is the force on the loop, so how much force is exerted on the loop? So force on the loop, it is given by mu naught I1 I2 by 2 pi r. Okay, so this is the formula. So mu naught I1 I2, when I say I1, you see I1 is the current passing through this wire which is given in the question, and a current which is passing through the first phase of the loop is 15 ampere, and current passing through that coil is of, you see that is also given in the question, that is of 25 ampere, right? 25 ampere current is passing through a wire, and 15 ampere current is passing through the one side of a circular loop. So how much force will be exerted on each other? So formula is F equals to mu naught I1 I2 by 2 pi r. So mu naught value will place 4 into 10 to the power minus 7. I1 is 25 ampere, I2 is 15 ampere, and length of the conductor, that is mu naught I1 I2, here we see L is also there, by 2 pi r. The length of the conductor is 25 centimeter, that means one side is 25 centimeter. So if you convert to meter, you will get 0.25. Total divided by 2 pi r. Now you see the distance between the wire and the circular loop, this distance here it is 2 centimeter, that means 0.02. So after substituting here, you will get the first answer. So this current carrying wire will exert a force of F1 on the first loop. Next, force on side 2 due to this wire, that is again same formula we will be using, mu naught I1 I2 by 2 pi r. So mu naught also remains same, I1 and I2 also remains same, and length of the conductor also remains same. what gets changes, that is 2 pi r. So you see the length of this rectangle is 10 centimeter, and here the distance between first face and this gap is 2 centimeter. So total distance between this wire and this side is 12 centimeter, that is 0.12. so substituting in this formula 0.12 here in place of R2, will get the other force. So the net force, now you see which force will be more. Definitely the force F1 will be more than force F2, because you see from the formula F is inversely proportional to R. So if the distance between the wire and the loop will be less, then the force will be more. So we see that this loop and this wire distance is only 2 centimeter, whereas this current carrying wire and this side is 12 centimeter. So therefore F1 is greater than F2. So we can find the net force acting on the loop, that is F equals to F1 minus F2. Substituting the values of F1 and F2 will get the resultant force, that is a current carrying wire will exert how much force on the loop, that is 7.812 into 10 to the power minus 4 Newton. So for this video only this much. So you need to write these numericals on your exercise book. Practice well and see you soon in my next video. Thank you.